Okay, welcome back. Lecture 2. We're gonna do some more counting. Okay. Actually, before I start, let me just make a quick comment that on the homework there were a couple of mistakes in the way that I stated the questions, and on the forum you can see the corrections. So, in one question, I forgot to say what the role of k was, I think. And in the other, anyway, maybe instead of me trying to remember right now what the errors were, just go to the forum and you can see the corrections. Okay, they're both there. And so we're gonna keep counting. We're gonna kind of start. Maybe move back a little bit. So last time we did this problem of counting tilings of a rectangle. And we treated this problem in several different ways just to give you an idea of the different approaches that we have in this class. And now I want to back up and actually start from scratch and talk about just very basic counting principles and go through some of the key things that we need to know how to count in this class. Okay. So here's two things that are both pretty obvious that maybe you have known since you were a child, but I want to make them explicit. Two basic counting principles. So, multiplication principle is about you trying to do two tasks, task A and task B. Now let's say that for task A, there are exactly little a ways of performing that task. Okay? After you perform task A, you go to perform task B. And no matter how you did task A, there are B ways of performing the second task, task B. Actually, I wonder if I have a red marker because, but I shouldn't do it on red because red doesn't show up on the video. But this is extremely important right here. So here's a little warning sign for you. Very, very important. This little part is the most common mistake in trying to apply the multiplication principle. Okay? So for task A, you should have A ways of performing it, and for task B, you should have B ways of performing it, no matter how you did task A. Should always be the same number of ways of doing task B. If that is the case, then the number of ways of performing both is A times B. Okay, and that's, when you think about it, kind of obvious because you have A possible outcomes of this, and then for each one there's B outcomes of the second one. So B plus B plus B, A times. I'm going to give you A times B. So this is when you want to perform two tasks. It says you have to perform A and B. The addition principle is for when you want to perform A or B, either task A or task B. If there's little A ways of performing task A, and if there's little B ways of performing task B, then the number of ways of performing one or the other is A plus B. Because you either did the first one, and in that case, there's A possibilities, or you did the second one, and in that case, there's B possibilities. Okay? So this is like case A and case B, and so you add the answers together. So these are two very basic principles, the multiplication principle and the addition principle, which we're going to be using over and over and over again. And so I want to make them explicit. And maybe just so you can see in a very easy counting problem how these are applied, let's say that I ask you the following thing. Let's say that I have some map, some country. I don't know, let's say that it looks like this, and then like this, and like this, and like this. Okay? This country has 4 states. Maybe I should say to the students in Colombia that states are American for departamento. Okay? Departamento 1, 2, 3, 4. State, and let's give them names. Maybe A, B, C, and D. Okay, these are the names of the states. And now you want to color the map. And let's say you have, I don't know, Q colors, some number of colors. 1, 2, and I want to color the map. So I want to give a color to each state, but Of course, you don't want to color neighbor states in the same color because then you won't be able to tell them apart in the map. Okay? Want to color the states so that neighbor states have different colors. Okay? And then the question is, how many ways are there to do this? How many such colorings? And let me just give you the name right away. These things are often called proper colors. Okay? You might be aware that this is kind of at the roots of combinatorics. One of the founding questions in combinatorics, or one of the very early questions in combinatorics, was to prove that no matter what map you have on the plane, that map can be colored using only 4 colors. This is now called the 4-color theorem. But here I'm giving you maybe more colors. You have 2 colors, and I'm asking you what's the number of ways of doing this. Okay? So let's do it. Let's say, for example, that so to color the map, what should we color first? Maybe it doesn't matter too much. Let's say that we color A. Okay. So how many ways are there of coloring A? Well, you have Q colors, so that means that you have Q possibilities. You can use any color for A. Okay. Now, next, let's color B. So how many possibilities do you have for coloring B? Well, in principle, you had Q, but I already used one of the colors here, and I shouldn't use that color. Okay. And so that means that now I have any of the Q colors except for the one that I chose for A. And you see this is very important because this answer doesn't depend on what color I chose here. The possibilities depend, right? If I chose to color A in blue, then the list of colors for B is anything but blue. If I chose to color green, then for B you can use anything but green. Okay? The possibilities are different, but the number of possibilities is the same. And that allows me to use the multiplication principle. Okay. How many colors do I have for C?
Q minus 2.
Q minus 2. Why? Because I should use, maybe we should say here, any but color of A. Okay. Here I get any but the color of A and B. Okay. Are these, how many colors do I have other than the color of A and B? It's not an entirely trivial question, because it's important to notice that A and B have different colors. Right? And so really I am eliminating 2 different colors. So out of the Q, I'm eliminating 2 colors. Finally, we color D. So how many possibilities are there for that? Well, we should use any color but the color of what? Well, for D, I shouldn't use the same color as A and C. So how many colors is that? Well, again, it's important to notice that by the way that I did this, I chose different colors for A and C. And so that means that these 2 really are different colors. And so I have Q minus 2 possibilities. Okay. And so, using the multiplication principle, I get that the answer is Q times Q minus 1 times Q minus 2 squared. Okay? that good? Okay. Now, what I want to show you is that, I mean, I asked you who to color first. And somebody said I should color A first. I want to show you that actually, even though I said that it didn't matter what I chose first, I want to show you that actually it does matter how we chose to do this. So I did prepare a class, and I did choose to label them A, B, C, and D to try to suggest to you that you should go in the order A, B, C, D. But let's do it in a different order now. Okay? Another way to do this would be the first color, let's say B. How many possibilities? Q possibilities. Then let's color C. How many possibilities? Q minus 1 possibilities, right? Anything but the color of A.
B.
Of B, I'm sorry. Now let's color D. How many possibilities do I have? For D, I should use anything except for the color that I used for C. So, I have Q minus 1 possibilities. And now let's finally color A. So how many possibilities do I have for A? Well, I should use anything except for A, I shouldn't use the color of B or the color of D. So how many colors is that?
Or C. Yeah.
Or C. Thank you. How many colors is that? Well, it depends actually. Because it might be that B, C, and D have different colors, or it might be that B and D have the same color. They're not neighbors, so they could be of the same color. And so here, this could be Q minus 2, or, write a little bit bigger. This is Q minus 2, or Q minus 3 possibilities. And so this is the red flag. This is when you don't want to use the multiplication principle. You can't say the answer is Q times Q minus 1 times Q minus 1 times Q minus 2, Q minus 3. The answer to this depends on what you did earlier. So this is when you cannot use the multiplication principle. So what do? Well, we discussed two possibilities. Either it's Q minus 2 or it's Q minus 3 according to two cases, case 1, case 2. And so, what you do in such a situation is that you just carry out the two cases separately. So, let's do the two cases separately. Case 1. B, C, and D have different colors. 3 different colors. Okay, so if B, C, and D have 3 different colors, what's the number of colorings? If I force B, C, and D to have different colors, well, B could be any color, C has to be a different color, D can be what? Q minus 2, right? Because they're supposed to have different colors, so here I should choose a color that's different from the previous two. Okay, so here I chose the color of B, the color of C, here I chose the color of D, right? And if I want B, C, and D to have 3 different colors, then I should choose 3 different things here. So this should be Q minus 2. And then finally, how many possibilities do I have for the color of A? Well, it should be anything that is not B, is not C, and is not D. And these 3 have different colors. So that means that the answer is Q minus 3. That's if B, C, and D have different colors. Okay? Now, what if B, C, and D don't have different colors? Don't have 3 different colors. So what's the number of colorings in this case? Well, let's first choose the color of B. Let's do it in the same order. So first B, then C, then D, and then E. So what's the number of colors for B? Well, for B I could choose any color. What's the color of C? For C, I could choose any color except for the color of B. What can I choose for D? Actually, I don't have a choice. If B, C, and D don't have 3 different colors, the only way to make that happen is for B and D to have the same color. So I don't have a choice here. D only has one possibility. And what about A? Well, if these guys don't have 3 different colors, that means that these 2 are of one color, this is of a different color, and so in total I have prohibited 2 colors, and so I should put Q minus 2. So that's the answer in case 2. Okay? And so then what do? I say, well, a proper coloring has to be of type 1 or of type 2. And actually there's no overlap between these 2 types. So therefore, the final answer is this plus this. So if I went in this order, then this analysis doesn't work. And the analysis that does work gives me that the answer is Q times Q minus 1 times Q minus 2 times Q minus 3 plus Q times Q minus 1 times Q minus 2. Should I be worried that I got a different answer? Maybe for a second, but if we did this in 2 ways, and if both ways are correct, then these 2 answers should be equal. And here they are, right? Because they have the common factor Q minus 1, Q minus 2 times Q minus 3 plus 1, which is Q minus 2. So this is equal to this. Okay. So you see, actually, this was an intelligent choice of an order to do this. And if I do a different order, well, I can still get the different answer, but it's going to require a little bit more work. Okay. This is one reason that I also wanted to show you this is that as you're solving homework problems, maybe you'll find that you use different procedures, and always the point is that for any kind of counting problem, there might be different ways of getting to the answer. But if you're doing it correctly, you should be getting the same answer. Okay. And for example, if you did it in this way that was a little bit less intelligent, and you did this, and then you realize, oh, actually, I can actually simplify this factors, and I simplify it like this, then maybe you should think, if the answer is this, then maybe this wasn't really the proper way of doing this. There should be a more clever way where I just have to take 4 decisions, and they have these number of possibilities. So very often, the answer can suggest to us what the proof can look like. And it actually happens very often in combinatorics that we come up with some stupid procedure to give the answer, and then once you see the answer, you say, oh, actually, that answer is a lot nicer than I expected. And it shows that there should be a nicer answer, and then you just hide your ugly procedure so that nobody sees it, and you look really clever by just showing your beautiful answer. This is what every textbook does, this is what every mathematician does. They hide all the ugly stuff, and they try to look really bright in front of you. So you should be aware of this, right? Sometimes the first answer is not the first procedure is not the best procedure, but it's a good way towards finding the best procedure. Okay. So this is one illustration of these principles, and now, actually, when I was preparing class, I thought about doing a coloring for a continent. But I decided that North America was too easy, and South America was too long to do in front of you guys. But so maybe for the forum, one good question is find the number of colorings of, well, North America is too easy, but South America is kind of an interesting question. So look at a map of South America. That way, if you're not used to it, you can even get a geography lesson out of this. And find what's called the chromatic polynomial of South America. Or if you're feeling more ambitious, try to find the chromatic polynomial of Colombia or the chromatic polynomial of the US. Okay. You can tell by the terminology, I'm calling this a chromatic polynomial. And in calling it a chromatic polynomial, I'm implying that it's a polynomial. This polynomial will come back later in this class. But it's a nice fact that no matter what map you started with, the answer for the number of colorings is always a polynomial. We'll come back to that later on. Okay. Let's count lots of things. So, actually, today I'm going to count a lot of things that maybe a good number of you have seen, but it never hurts to go over things that you've seen before. So let's count permutations. So sometimes this is called Sn. This is the set of permutations of n. Right away I want to introduce this notation. I'm going to be using this all throughout the semester. This just means the set of numbers from 1 up to n. Okay. So I want to count the number of permutations of n, and so as you probably know, the number of permutations is this number n factorial. The number of permutations of n is n factorial, which is the product of the numbers n and minus 1 and minus 2 up to 1. So again, if you have a combinatorics problem and the answer is a product of things, this is good news. This means there's probably a proof that explains each factor one by one. So there's a couple of ways of doing this, but maybe the most natural is to say, okay, to choose a permutation pi 1, comma, pi 2, up to pi n. Here I'm just using one line notation, so this is just some reordering of the numbers from 1 up to n. So what I do is I just first choose the first one, choose pi 1, and of course any number could be in the first position. Okay. Then I choose the second one. And no matter what number you put in the first position, the number of possibilities for the second position is n minus 1, because you should put any number except the one that you just wrote down. So n minus 1 possibilities. Then you choose pi 3. And so now you should choose whatever number except for the two that you just chose, which are different because this is a permutation, and so forth. Up until when you go to choose pi n, there's only one possibility, which is the only number you haven't used. So that means that in total, again, to choose a permutation, you have to make all of these choices. It's not that you choose one of them. You have to choose who goes first. You have to choose who goes second, who goes third. So you have to make all of these decisions. Each answer doesn't, so the number of possibilities of each answer doesn't depend on the previous ones. And so you can just multiply all of these numbers and get. Okay. So that's how you compute the number of permutations of 1 up to n. Okay. Now let's talk about subsets. So let me just write a notation here. 2 to the s is the collection of subsets of a set S. And so here, this is a capital S. Okay, so S is a set. And capital S, choose lowercase k, is the collection of k subsets of S. Okay. Where k is a number, and I mean the subsets of size k. So the first proposition, again, one that I think all of you know, is that, so let's say that let S be a set of size n. Some finite set of size n. So then the number of subsets is 2 to the n. Okay. As I said, in this class we start counting slowly and then we go faster and faster. So let's do this without too much of a hurry. Again, this is a product of n 2's. Okay, and so there must be a proof that tells me, okay, I just need to make n binary decisions. So to do that, let's say that my set S is given by elements a1 up to an. So then to choose a subset, what I have to do is one way of choosing a subset is saying for each element, is that element in or is that element out? So I need to choose. Is I1 an element of my subset? The answer is yes or no. 2 possibilities. Then you say, this is my second element in my subset? 2 possibilities. Independent of the first element. And so on. And possibilities. Sorry, 2 possibilities. So in total, I just multiply these numbers, and I get 2. So that's why the number of subsets is 2 to the n. And let me just point out that what I just gave you, this gives a bijection between the subsets of S and the sequences, let's say, I don't know, E1 up to En, where EI is 0 or 1. Right? E1 is going to tell me, is element A1 in or is it out? If it's in, I put a 1. If it's out, I put a 0. So, remember, a bijection is a one-to-one mapping that maps to each one of the elements here, one element here, and vice versa. Okay? It's injective, it's surjective. It's a bijective mapping. Okay. So we've counted all the subsets, but now we want to count the k subsets. Okay. And let me make the definition. Let me define the number and choose k to be the size of the set S choose k for the subset of size for a set of size n. Okay. So in other words, the number of k-subsets of an n set. Again, maybe it's worth getting the language for this thing. So in English, we say n choose k. At least in the US, that's what people say. In Spanish, n con k. Or sometimes n combinado con k. The shortest is n con k. Okay, so what I want to do is give a formula for n choose k. Okay. So let me do it in the following way. To choose a k subset b1 up to bk of S, what do I need to do? Well, let's choose B1. So what's the number of possibilities? Well, I have an n set, so B1 could be anything. Then let me choose B2. Okay. And B2 could be anything except for the guy that I already chose. And so on. Okay, until I choose BK. And for BK, I can choose any of the things that I haven't chosen. Okay, I already chose k minus one of them. So I get n minus k plus 1. So then I multiply all these numbers, and I get n times n minus 1 times n minus 2 up to n minus k plus 1. Okay. And I can rewrite this as taking n factorial, right, the product of n up to 1, and then removing the ones from n minus k up to 1 by okay. Am I done?
You counted too many.
So again, I want you to see a wrong argument, and then I want you to recognize that it's wrong. So why is this wrong? Well, because I said choose B1, choose B2, choose B3, choose BK, but I'm choosing a set, right? And so the set does not come with an intrinsic order. In other words, if I chose 2, then 4, then 1, that would be the same set as if I chose 1, then 4, then 2. But I counted those as different outcomes of this procedure. So I overcounted. Actually, what I counted here is the number of ordered k-subsets. Which is not what I want. I want the k-subsets, not the ordered k-subsets. So this is not my answer. Okay. But it's useful because what I'm going to do is I'm going to count this in a different way. So to choose an ordered k-subset of S, one way of doing it is to choose the first element, then the second element, and so on. A different way to do it is to first choose which k elements I'm going to use, and then order them. So first I can choose an unordered, let's let's say choose the underlying unordered k-set and then order it. And I'm going to hope that the answer to this doesn't depend on the answer to this. So what's the number of ways of choosing the underlying unordered k-set? By the very definition, this is what this number means. And choose k possibilities. And choose k means the number of unordered k subsets. Okay. And how many ways are there to order this unordered thing? Well, this is just a permutation of that k set, right? So to order it, I have k factorial possibilities. And so that means that the number of ordered k subsets is equal to this times this. And choose k times k factorial. Okay. So then what happens? Well, as I told you, we're answering one question in two different ways. And each way is correct. This procedure was correct, this procedure was correct, and therefore our answers must be the same. And if our answers are the same, that means that n factorial divided by n minus k factorial should be the same thing as n choose k factorial. Okay. And so that gives me a formula for n choose k. N choose k is going to equal n factorial divided by k factorial times n minus k factorial. So first we do it wrong, but then we realize that actually this alternative problem, this related problem, is useful to our problem at hand. And it ends up being the auxiliary problem that allows us to give a formula. Okay. You might be aware that these are called the binomial coefficients. Okay, so we talked about last time we talked about how often generating functions are a very valuable tool for counting problems. And so what I want to do next is try to treat the same topic now through generating functions. So we're talking about subsets. Let's talk about subsets and generating functions. You should get used to, like, very often, we're just going to write GF for generating functions. So, how do I talk about subsets in terms of generating functions? So remember that, we can think of generating function as some kind of formal algebraic expression that keeps track of our combinatorial objects. Okay? So let's talk about the multivariate generating function for subsets of n. So let me write this down, and then we'll do an example of what this is supposed to mean. So what I'm going to do is that I'm going to sum over all the subsets of 1 up to n. So each set is going to give me one term, and each term is going to be a monomial. which is just going to tell me what are the elements of that set. So I take a product over the elements of that set, x of that kind. Okay. This might seem complicated, but it's not. So for example, for n equals 2, what am I doing here? I take all the different subsets. So for example, let's consider the subset 1, comma 2. For that subset, I multiply the terms x1 and x2. Okay? And so I have a monomial that represents algebraically my set 1, comma 2. Okay? But I have a different subset which is just taking element 1. And so that just is represented by the monomial x1. And then I have a different set which is represented by, sorry, the set 2, the subset 2, is just represented by x2. And finally, the empty subset is given by an empty product, and by convention an empty product is equal to 1. Right, so this represents 1, comma 2, this represents 1, this represents 2, and this represents the empty set. Okay? So it's just some algebraic expression that is kind of an algebraic way of listing all subsets. Okay, now, you're mathematicians, I hope that this expression makes you a little bit antsy and you want to do something to it. What do you want to do? It factors. How do you factor it? x1 plus 1, x2 plus 1. So is this part of a general phenomenon? It turns out that it is. This is equal to 1 plus x1, 1 plus x2, up to 1 plus x. If you read this in a book, it's just going to say clearly. Boom, that's it. Is it clear? Well, if you think about it for a little while, it will become clear. Look at the right-hand side. How do you multiply this thing out? Just consider every possible, when you multiply all of this out, you're going to get a bunch of terms, and how do you get a single term? Well, a term comes from multiplying one of these guys, one of these guys, one of these guys, and so on. But when you choose 1 or x1, you're saying either I don't choose element 1 or I choose element 1. Here, I don't choose element 2 or I choose element 2. So on, I don't choose element n or I choose element n. Okay? And so the monomials that are going to come out of this are exactly just products of some subsets of the x's. Okay? So this is the kind of thing that, again, a book might just say by inspection this is true. If I hope that what I'm saying at least makes it plausible that this is true, and if you don't entirely trust me, then you could prove it by induction, and you'll find that it's actually pretty easy to prove by induction. It's actually kind of clumsy to prove it by induction, but anyway, you can do it. So anyway, this is the multivariate generating function for subsets of 1 up to n. Why is this useful? Why is it a good thing? Well, maybe let me put a box around it because this is a nice identity. It's an identity of polynomials and n variables, actually. And now let me plug in x1 equals x2 equals dot 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 equals xn equals x. So I'm just going to set all variables equal to each other. So what do I get here? I get the sum over the subsets of n. What do I get here? X times x times x times x. How many times?
Size.
X to the size of a. And what do I get on the right hand side? 1 plus x, 1 plus x, 1 plus x, 1 plus x to the n. Okay. So maybe you can see where I'm headed with this. Let's leave this side intact. And now let's say, okay, how many terms here are equal to x to the k? I'm going to get an x to the k whenever my set A has size k. How many times does that happen? It happens exactly n choose k times, right? There's exactly n choose k subsets of size k which contribute an x to the k. And here k ranges over all possible values of the exponent here, which goes between 0 and n. So you get this very familiar formula, which is the binomial. Okay. And okay, so that's a nice combinatorial proof, and I hope you see that these are more or less the same statement. And if you want to give a combinatorial explanation for this, sometimes it's given just in terms of this one, but I think this is a little bit clearer. You instead do it in this multivariate sense. Okay. So we get the binomial theorem almost for free from the generating functions. Let me make a little note here. That we have given two proofs of this identity. The second proof is that, right? This is an identity of polynomials. There's no convergence issue. These are just polynomials. You can plug in anything you want into a polynomial. So plug in x equals 1, and you get this. So that's an algebraic proof. But we also give a combinatorial proof, because this is the number of k subsets of a set of size n. And so if you add over all the different values of k, you're going to get all the different subsets. So the total number of subsets is 2 to the n. So we get this via combinatorics and via algebra. And let me give you again a simple exercise for the forum. Will be to show a similar identity, but with a k in front. Actually, maybe I'll just let you figure out what this is. If you really don't want to see the answer, then don't look at my notes, because I did write it on my notes. Okay. But I think it's a good exercise to just try to figure out what this is equal to without knowing what the answer is. And you should try to give a combinatorial proof, and you should try to give an algebraic proof. Okay. So, what did we do? We started with permutations. We computed permutations. That was easy. We talked about subsets. And now I want to talk about compositions. So, a composition of n is a way of expressing n as a sum of positive, as an ordered sum of positive integers. Okay. So for example, let's talk about the compositions of 4, or let's just do 3. So what are the compositions of 3? Well, you need to write 3 as a sum of numbers, positive integers, so you could have them be all equal to 1, or You could write 2 plus 1, or you could write 1 plus 2, which is different because these are ordered things. Or 3. Okay. And let's define a K composition is one with K parts. And a weak composition is an expression where you allow non-negative integers. So such an expression as a sum of non-negative integers. Okay, so the only difference between weak and normal is that 0 is allowed. 0 allowed. Okay. So we're going to count compositions. Let C of n be the number of compositions of n. Okay. Maybe we can do a little table here. So for 3, we saw that the number of compositions is 4. What's the number of compositions for 2? Well, 2 is either 1 plus 1 or 2. And for 1, well, the only way of writing 1 as a sum of positive integers is just to use the number 1. Okay. There's different ways of doing this. And again, in the interest of seeing different approaches, let's talk about using a recursive approach here. So how do we count compositions of n recursively? Well, we talked about how one thing that you can do is you can say, okay, let's take a composition of n and see what happens at the beginning. Okay. Let's say the first number is something. If the first number of a composition, if the first number is k, then what's the number of ways of completing the rest? First number is k, then what are the what's the number of ways of completing the rest of the composition? It's just C of n minus k, right? You just have to split the rest of the sum. So there are C of n minus k compositions. Okay? And so we might try to say, okay, well, maybe we can do a multiplication principle here. So what's the number of ways of choosing the first part? Well, the first part could be 1, 2, 3, 4, anything up to n. Okay, so there's n ways of choosing the first part. Now, what's the number of ways of choosing the rest of the composition? It's C of n minus k. So is the answer n times C of n minus k? Okay, at least I see you guys going, no, that sounds horrible. Why is that not the answer? Because this depends on k, right? The answer to this question is dependent on what you did in the first step. And so that's why you cannot apply the multiplication principle. What you have to do is that you have to split by cases. What if k is 1, what if k is 2, what if k is 3, etc. Okay? So that's what we do. So what if k is n? How How many compositions are there? C of 0. C of 0. What's the C of 0? Let me think about that for a second. What if the first part is n minus 1? Then the rest is C of 1. What if the first part is n minus 2? Then for the rest I have C of 2 compositions. And so on. What if the first part is 2? Then I can do the rest in C of n minus 2 ways. And if the first part is 1, then I can do the rest in C of n minus 1 ways. Okay, so these are the different cases for what the best first part could be. And this is the number of possibilities in each case. Now you're not going to do everything at the same time. These are separate events, right? You just have to choose one of these things. What happens is exactly one of these possibilities, and so what you do is that you add up all these numbers. Okay. And so, what did we say C of 0 is?
Negative 1.
Well, maybe instead of using C of 0, which is a little tricky, let's just say, if k is equal to n, how many compositions are there? If the first part is n and you're trying to add up to n, then you're just looking at one part which is equal to n. So let's just say that there's one part here. And so what I just showed is that C of n is equal to C of n minus 1 plus C of n minus 2 plus C of n minus 3 up to C of 2 plus C of 1 plus 1. That's my recurrence relation. This is true for any n greater than or equal to 2. This argument works. Okay? Okay, so I have a procedure to compute these numbers. Let's compute the next one. So what's C of 4? It's telling me I'm supposed to add up the previous numbers and add 1 to the result. 4 plus 2 plus 1 is 8. C of 4 is 4 plus 2 plus 1 plus 1. What about C of 5? 8 plus 4 plus 2 plus 1 plus 1? 16. The next one, add these guys up, add 1, 32. Okay, so you see what the answer is what? 2 to the something. 2 to the how much? 2 to the n minus 1, right? For example, this is 2 to the 5 minus 1. Okay. Okay, so do we have a proof? Well, we essentially do. If you think this is true, and you prove this recurrence, you won't have a hard time proving this. Because by induction, you can say, well, assume that this formula is true for all the smaller guys, then C of n is going to be 2 to the n minus 2, plus 2 to the n minus 3, plus 2 to the n minus 4, etc., plus 1. That's a geometric series, and you'll see that the answer is this. So that's a proof. Okay? But again, I hope that you see, when you get an answer like this, you should realize that this was not really the best proof. There should be a better proof. And so what we want to do is give a better proof of this. But I wanted to show you another proof which was fine. I mean, it's not an ugly proof, right? It was kind of clever. We did some work. We got it. There's nothing wrong with this proof, but there should be a better. So, proposition. There are 2 to the n minus 1 compositions. Okay. So we have one proof by recursion and induction. But again, you'll never see this proof in a book, because in a book they're just going to show you the slickest proof. And there is a very slick proof. Which is the following. To choose a composition of n, again, you know what the proof should look like. We should be making n minus 1 decisions, and each decision should be a yes or no question. So that you get 2 times 2 times 2 times 2. So, first step, write n equals 1 plus 1 plus 1 plus 1 plus 1. Okay. Then delete some of the pluses. You can choose which ones to delete. All of them, none of them, something in between. And then group all the ones into parts. Okay, so let me give you an example of what we're talking about here. Let's say that it's 8. I do 1 plus 1 plus 1 plus 1 plus 1, 1, 2, 3, 4, 5, 6, 7, 8. Now, I delete some of the pluses. So which ones do I want to delete? Well, I can choose any of them. Let's say that I take this one and delete it. I take this one and delete it. And let's say that I take this one and delete it. And maybe this one. And what do I get? I get an expression where I get 1 plus, now I group these three ones into one part. Then these two get grouped into one part. And these two get grouped into one part. I'm realizing this is a little bit hard to see. And since this is video, people can even rewind. So let's not do it as a movie. I said delete them, let's delete them. So let's actually just delete these things, and then it'll be a lot clearer, a lot easier to see. 1 plus 3 plus 2 plus 2. And that's a composition. Okay? So what did we just do? Well, this is a bijection between compositions of n and subsets of the pluses. Bijection between subsets of the n-1 pluses and compositions of n. And this is a set of size n-1, so it has 2 to the n-1 subsets. And so this is a much better proof that this is the number of compositions. So like they say, hindsight is 20/20. Once you see what the answer is, you can go back and come up with a much nicer proof. But this is a very clever proof, and often they give you the proof without showing you the answer. I mean, once you know the answer, maybe the proof is not so ingenious. But without knowing what the answer is, the proof seems very ingenious and out of nowhere. One advantage of this proof is that I can strengthen it. So for example, I can find what's the number of k compositions of n. Compositions into k parts. Well, I just have to make sure that out of my n-1 pluses, I keep how many? If I want k sum n's, I need k-1 pluses. And so this bijection maps k subsets to k compositions. And so that gives me okay. So this counts compositions. Let me now use this to count weak compositions. leave room for the answer. What's the answer? What is the number of weak compositions of n? The question is sillier than it might seem.
Infinitely?
It's actually infinite for a very silly reason, which is that you're allowed to use zeros. And if you're allowed to use zeros, then you can use as many zeros as you want and create different compositions, different weak compositions. So I have no hope of answering this. I mean, okay, there's the answer, infinitely many. But what about k compositions? If I have k compositions, then you can't put zeros indefinitely. You can put at most k minus 1 zeros. So then this is a finite number. So maybe we can do the proof and then see what the answer is. So if I take a weak composition, this is a weak k composition. Again, there's different ways of arriving at the answer. And once you know what the answer is, it's easy to come up with this argument. I mean, I'll tell you what the answer is. N plus k minus 1, choose k minus 1. And once you know what the answer is, which again you could have arrived at by a less clever method than what I'm about to do, maybe by recursion or something else, actually it's pretty easy to say, well, you know, this looks a lot like compositions. And maybe there's a relation between weak compositions and normal compositions. How do I get a non-weak composition out of this? Well, one thing I could do is just bump each part up by 1. If this is a weak composition, then these guys are greater than or equal to 0. So when I add 1 to them, they become positive. And if these guys are positive, then if I subtract 1 to each part, I get a weak composition. So this is actually a bijection. But what's the result here? It's not n anymore, because I added k ones, and so I get n plus k. And so I have a bijection between the weak k compositions of n and the normal k compositions of n plus k. And I already counted those. So I get this from. So that gives me. Okay. Any questions about that? So this ends at 3:25, right? I always get this. I always forget. This is okay. So I guess that means that the class is basically over. Maybe one thing that I wanted to mention before we go is that so I haven't said this very explicitly, that in the course I'm essentially going to be following Stanley's books, and I'm going to be doing much more of EC1, Enumerative Combinatorics 1, than I'm going to be doing of EC2. For example, what I did today is essentially section 1.2 of Stanley book. Now, I'm going to try to be good and tell you in each class what section we're doing, but it might not match exactly. So for example, last time I covered EC1 section 1.1, except that you'll see that there's actually no mathematical overlap between what I said and what Stanley says in section 1.1, but I was trying to convey more or less the same points. Okay? Sometimes it's useful when the professor doesn't just repeat what's in the book. In this case, there's, I think, no overlap in the content, but the message is the same. And so I very much encourage you to read Stanley's section 1.1, which will supplement what I said last time. Today I was a little bit more faithful to a lot more faithful to what he does. So today was pretty close to section 1.2. Last time was the same spirit as section 1.1 in the book. And I'll keep you updated as we progress along. The other thing I'll say is that I updated the texts section of the website. So we talked about how this book isn't exactly easy reading. It's a great book, but if you are looking for books that are a little bit friendlier, then I wrote down a few more options of kind of supplementary books that you could look at. So let's stop there. Oh, the other thing. I'm flying to Colombia on Thursday. So actually, we're not meeting on Thursday because I'll be on an airplane. And I'm teaching there in their schedule, and then you guys will meet here in your usual schedule. So there's no class on Thursday. And then for the next week, I'll be in Colombia, and you guys will be here watching on video. And I want to ask for a volunteer that will help me set this up. It's actually very easy. But it'll be on YouTube, and all you have to do is go on YouTube and project the video there. And you guys will meet and watch the video here as they usually do in Colombia. Okay. And we'll have office hours over Skype like they usually do. And any other questions you can ask me electronically. So I'll be gone for the rest of this week and next week. And then I'll be back here. All right. So volunteers, who's going to volunteer? We're not moving until somebody volunteers. You can do it? Okay. Thank you, Kristen. Actually, has anybody used this projector before? Oh, you have? Okay.